Okay, so supposing we make this mapping here, then let's see what happens to the electromagnetic field tensor. And of course we know that derivatives distribute. And if I just change notation briefly, remember that this comma is just the same thing as a derivative. And so you can see here we have exactly the same term except the derivatives are in different order. And of course, because derivatives commute, that means that this cancels, and we're left with that, which is exactly our old electromagnetic tensor. So even though we've added this term to our forward potential, we have not changed the forces acting on any charged particles at all, because we get exactly the same electromagnetic tensor. All right, what about Maxwell's equation? Let's just calculate what this is. And again, derivatives distribute, so we've got, and once again, you'll see that these terms are equal and opposite because I can change order, and then left with this term here, which is precisely, of course, exactly the terms we had in the original Maxwell's equation, and so Maxwell's equation is unchanged. And so the new derivatives of the new forward potentials are still equal to mu naught J mu. Now, whenever we have a transformation that doesn't change things about our physics, we should immediately be thinking along the lines of conserved quantities, a la Noether's theorem. We'll examine that over the next couple of lectures as we bring together all the major sections of this course. We'll revisit quantum mechanics and see what changes we have to make to ensure that it obeys the principles of special relativity. Making quantum mechanics Lorentz invariant heavily restricts potential theories, and we should get at least a glimpse of why the universe behaves the way it does. Requiring both Lorentz invariants and symmetries in the Lagrangian led theorists over the last century to do something quite new to the normal process of science as it was established over the previous few centuries, and that was postulate the existence of things that had never been seen experimentally. It's kind of doing science backwards, if you will. And that was a recurring theme in physics throughout the last century, and most recently culminated in the discovery of the Higgs boson. And I hope to give at least a flavor of that discussion and a flavor of that discovery over our last few lectures.